if you're looking at the wheel kind of from the side like this, the front and the side, the disc brakes have a pad that presses against the disc like that. And they're safer because they don't heat up and fail to function. Well, anyway, that's a long story that I didn't intend to tell, but the reason that a car stops when you press on the brakes is because of the friction. Okay, the ultimate friction is when the car runs into a brick wall.
Yeah.
You know, ultimate friction, brick wall. Friction slows down moving objects. Now, here, I'm going to erase this. I'm assuming you have this.
Yeah.
And if you don't have it, get it from somebody else, because I want to write the rest of the conclusion up here. I'm going to add one sentence to the conclusion.
Wow.
Okay, add this to your conclusion. This is going to be a universal law of physics. Physics is a study of forces in motion that you'll take if you take physics in high school and college. And I'm going to put it in parentheses because it's not revealed directly by the data, but it's related to the data. An object, add this now, an object that is in motion will stay in motion unless it encounters friction. Universal law of physics that affects your life every day. Every day something happens in regard to that universal law that affects your life. Well, friction has to be between two things. When you rub your hands together, it's between your two hands. Where's the friction in this experiment? See, the car is obviously encountering friction or it wouldn't slow down. Where's the friction? Between what two things do you think is the friction, Allie?
The car and the tires.
You're close. You're close. Who else wants to try? Tanner?
Tires and the rim.
The tires and the tape. All vehicles, all wheeled vehicles, have friction between the tires and the pavement. Bicycles, motorcycles, trucks, cars. Okay. And of course, if you stop applying the fuel, the energy in the form of the fuel, they'll eventually slow down and stop because of the friction. You can keep an object going even though it encounters friction if you apply fuel, energy through fuel. Okay? Well, let's turn this around. If an object that is in motion doesn't encounter friction, it'll stay in motion forever. Raise your hand if you can name something that stays in motion forever, has been moving forever, and will continue to move forever because it doesn't encounter any friction. Emily?
The sun?
No, well, maybe, but that's such a big picture that it's hard to understand. What's something smaller than the sun that's been moving forever, Jeremy? The Earth around the sun.
It's a million.
All planets around the sun. Why don't they encounter any friction? Anybody know why they don't encounter any friction? Why, Jake?
Because there's nothing to stop them if
There's nothing in space to be a friction with. Okay, now, what's something closer to the Earth than the other planets that goes around the Earth and as far as we know has been moving forever and will continue to move forever? Something that goes around the Earth. What? No, the sun doesn't go around the Earth. The Earth goes around the sun. What, Emily? The moon. Okay, I'm going to draw another diagram here. Let's say this is the Earth, 8,000 miles across. It's surrounded by the atmosphere, the air. And who remembers how thick the air is, the atmosphere? Anybody remember in miles? Do you remember, Chase?
60.
63, yeah. 63 miles. Okay. Well, it's obviously not drawn to proportion because if this was drawn in proportion, the atmosphere would be a green line right next to the black line. But I want to use this space to draw some things. Now, the moon is up here, and it's not necessarily up. The moon is out here, 240,000 miles away, and it's about 2,000 miles in diameter. Okay, well, it's been going around, it's 240,000 miles away. 240,000 miles to the moon. Average. Well, as far as we know, it's been going forever and will continue to go forever. Why? Why? Why, Jeremy?
No friction.
No friction. Nothing up there to cause friction. Okay, now who can name something that's closer to the Earth than the moon that is going around and around and theoretically will never stop? Jake?
The atmosphere.
No. No. It's something that's above the atmosphere. What's above the atmosphere going around and around and theoretically will never stop? Stevie? Jake? Jeremy?
Satellite.
A satellite. The first satellite was launched in 1957. It was called Sputnik. It was named after the dog of one of the astronauts. These were Russians launched it in 1957. I remember it well because I was teaching biology at Bellevue High School, and I remember the news coming in over the public address system that the Russians had launched a satellite. The moon is a natural satellite. The satellite means it goes around. Okay, well, in 1930, Albert Einstein predicted that it was possible to launch an artificial satellite, but he didn't have the capability to do it. It wasn't until 1957 that it was done, and here's why.
It took them.
When something is in orbit, like the satellites or the space shuttle, gravity's trying to pull them back. So to keep it in orbit, you have to create an opposite force equal to gravity, and that's called centrifugal force. Now, you've all experienced centrifugal force if you filled a bucket partly full of water and swung it like this, and you know that if you swing it fast enough, the water doesn't come out because you're creating centrifugal force. Okay? So they have to create a centrifugal force or artificial gravity opposite Earth's gravity to keep it in orbit. The only way they can do that is to get it going 18,000 miles per hour. Okay, well, somebody ought to figure out now why Einstein wasn't able to put an object in orbit. Why wasn't Einstein able to put an object in orbit even though he said it could be done? Why, Wyatt? Why, Jeremy?
Because it probably didn't have the machine that could make it go.
Nobody had a rocket that would go 18,000 miles per hour until 1957. The Russians did it, then we did it a year later in 1958. Okay, if you get it going fast enough, at 18,000 miles an hour, then the centrifugal force balances the gravity and will keep it in orbit, and theoretically it will stay up there forever. Now, we also put the space shuttle. We put the space shuttle up in orbit. And it's going around the Earth. How fast is it going? How fast is it going, Chase?
18,000.
At least 18,000 miles an hour. All right, well, theoretically it'll go around forever. But we don't want it to go around forever because we want the astronauts to come back after about 2 weeks. What do we do to get it back? Can anybody figure out what we do to get it back? What do you think we do to get it back, Mason? Don't turn it around. No, don't turn it around. What do you think we do, Tanner? What do you think we do, Jessica?
Hit on the brakes.
Huh?
Hit on the brakes.
How? We create friction. How?
Sitting on
Jay?
the brakes. Because
if you go fast enough, they have, this is what I've heard, they have these flaps they put out, and it's kind of like a brake.
Flaps don't work in space.
Oh.
Flaps only work if there's air to cause resistance. How do we get it back, Jonathan?
Shoot fire off the other end and make it.
Oh, you're very close. In the nose of the space shuttle, there's a little rocket called a retro rocket. Retro means reverse, okay? Now, they're not very big. They're about the size of a fire extinguisher, and they're made in Redmond, Washington. And they don't have much force. So let's say, I don't know exactly, but let's say 10 pounds of force. Well, you wouldn't have to push very hard to get 10 pounds of force against something. But here's another universal law of physics that I'm not going to write down. But I want to tell you about it. It's this. For every action, there's an equal and opposite reaction. Now that's why a rocket works. For every action, there's an equal and opposite reaction. A rocket doesn't push against the ground. It doesn't push against the air. It creates a force in one direction on the body of the rocket, so there's a force in the opposite direction, making the rocket go forward. Okay, so if 10 pounds of pressure comes out of this retro rocket, it creates a force of 10 pounds in the opposite direction on the space shuttle and causes it to slow down. Well, if you slow down an object in orbit and get it below 18,000 miles an hour, what'll happen? What? Well, it'll come down. Okay, so they fire the retro rocket, and then the space shuttle goes around in a gradually falling path like this, and enters the Earth's atmosphere about here, let's say. When that rocket going 18,000 miles an hour hits the atmosphere, the air, there's a lot of friction, and friction causes a lot of heat, and there's a big flame. Now the space shuttle would burn up from the heat if it didn't have heat absorption tiles on the front. How many of you have ever seen a picture of the nose of the space shuttle and seen the tiles that are on there? They're designed to burn up so that the shuttle itself won't, see. Now if you were right under here on this side of the Earth, and it was at nighttime, you'd see that big flame. Then it enters and it gradually declines and takes a falling orbit, and then it'll eventually wind up over here at Cape Canaveral where you want it to land. Now this requires a lot of precision, extreme precision. If you want to be in the space program, you're going to have to take every math course that any university teaches, probably. Here's why. Suppose that exactly 10.0000 pounds of force is needed to make this shuttle land where you want it to. Well, if it's 9.999 or 10.001, 1/1000th off, it won't land where you want it to. Instead of landing at Cape Canaveral, it might land up in the Himalayan mountains or out in the middle of the Pacific Ocean or something. So that kind of precision can only be arranged with computers. Not only that, but you need to know how long to fire it. And you need to know when to press the button to fire it. They press the button from the ground, okay? Well, let's say that you need to press the button to fire the rocket for 3.8 seconds. Well, 3.9 seconds or 3.7 seconds. It won't land where it's supposed to. So all that precision requires computers, and that's another. Well, here's something that's related to that. We put a satellite in orbit in 1957, the Russians did, but they didn't intend to get it back. They didn't want to get it back. But we want to get the space shuttle back, and we didn't put the space shuttle up until many years later, because we wanted the space shuttle to come back because it had people on board, and in order to make it come back and land where we wanted to, we have to have all this precision with how long to fire the rocket, how much force to fire the rocket, and those things can only be controlled by computers. Okay, so now I don't require you to draw this. If you do, you could draw it on the back of your paper, but if you don't have colored pens or pencils, it would be awfully difficult to figure out. So if you wanna do it, it's okay. All right, now, oh, I forgot to draw a couple of things. If there's a car traveling on the surface of the earth, there's friction between it and the ground, or the pavement, okay. If there's a plane flying up here, a jet plane flying up here, where's the friction? Between the plane and what?
The car?
No, the air, yeah. See, planes only fly in the atmosphere. They don't go above the atmosphere. You need a rocket to go above the atmosphere. All right. Well, if you so the friction is between the plane and the air. And if you don't believe that air can cause friction, try holding a cardboard box out the window of a car going 60 miles an hour. It'll blow it right out of your hand because of the friction. Okay. So the friction is between the plane and the air. Now, the ground causes a lot more friction than the air does, so you can get a lot more. You can go a lot more miles in an airplane on a gallon of gasoline than you can go in a car on a gallon of gasoline because there's a lot less friction. So that's an important thing. All right, now here's a practical application of this concept. Do any of you have a relative that's an independent trucker? Somebody that has a truck and hires out their services to haul cargo? Well, there are a few independent truckers around. See, most companies have their own trucks and their own trucks carry their cargo, but there are some people called independent truckers that have a truck and then they hire out their services to companies that want cargo hauled. Well, let's say that you're an independent trucker living here and a lumber mill from Tacoma calls you up and says, I've got a load of lumber I want you to haul to Portland for me. How much will you charge? What's the first question the truck owner asks the lumber mill owner? What does he want to know before he'll tell him how much he'll charge? What does he want to know, Jackie? How heavy it is. Why does he want to know how heavy it is? Why?
There's a law that if you haul.
Okay. What he's trying to say is, more weight causes more friction. More friction requires more fuel. Why is that important to the truck owner, Emily?
Because he'll have to buy his own food.
He's in business to make a profit, and if he figures that it's going to take more gasoline and dollars of gasoline to haul the lumber than they're going to pay him, he won't take the job. All right, now here's a problem for you to figure out mentally. It shouldn't be too hard for you. Suppose they call you up from the lumber mill one day and 1 week, and they say, I've got this load of lumber that weighs 10,000 pounds. And then the next week they call up so you take the job, and then the next week they say, well, you did fine work, we've got another load, this time it weighs 15,000 pounds. Which one is the trucker gonna charge more to haul? Which one? 15,000. Now, here's another one. Suppose these trucks have 100-gallon gasoline tanks. That's pretty typical for a truck. So at the mill,